Let's start. First, I need to thank your journal and you for inviting me to give this webinar. Of course, I prefer to be invited to be in Brazil to give a real seminar, but still, it's a very nice thing of you to having invited me. When you invited me, I was an open invitation, so I had no real idea about the subject that you prefer for your webinar, so I had to take some decisions. And finally, I decided to talk about trace element analysis in the environment, but also to put that into a particular context, which is that of analytical chemists as providers of good data in our world. As you know, we are in a special situation. It's a special geopolitical situation everywhere, with a lot of science denial going on, favoring controversial point of views that are not really based on real or in good science. And I think that it's, in a way, our role to try to provide good data, because finally denied facts are still facts. So we need to be sure that these facts are based on good and reliable data. And this even more nowadays in these times of artificial intelligence, where all the models have to be based on data that they gather everywhere in a legal and an illegal way, it doesn't matter. But if the data is not good, what their systems are going to provide us will not be good either. So we're in times where I think that analytical chemistry, that at least in some countries, is like here in Switzerland, tends to be considered as a second-class science. I think that analytical chemistry has an important role to play in this world. And this is because analytical chemistry, I just took this definition from ACS, but it doesn't matter the exact definition of analytical chemistry is, because you all know. But I would like to focus on two words that are in this definition. One is that analytical chemistry is about obtaining data, but it's also about communicating the information that this data provides. So we are not just obtaining, but also communicating. So in a way, we are data providers in a very large sense. So we need to be sure that we are able to provide reliable data and that we are able to communicate this data in the best possible way. So the examples I'm going to deal with today are all related to trace element analysis and in the environment, because it's where I'm mostly working myself. The talk will be divided in 3 different parts. One big one, which is the part 1, and then 2 smaller ones later. And the first is about the need for new analytical methods that respond to real needs. Why this? In 2009, I was surprised by something, and it's the following. I was asked to give some advice on bismuth, which is an element that is not very common, let's say. So I went to look for data. And so I went to the data provided by the big European project of all the European geological surveys that took about it depends on the media, but let's say about 1,000 samples all over Europe, about nearly all the elements of the periodic table. And this, you have here the data for bismuth, and you see that most of Europe is covered in blue. And blue means that you have concentrations below 2 nanograms liter, which happens to be the detection limit. So in fact, what this nice map shows us is that we have 50% of the data below the detection limit, which is really not a very satisfactory situation. And it was I was even more surprised when I tried to look at the publications of new methods to analyze bismuth in natural waters. And I went through all the publications from 2000 to 2010 in analytical journals. And I guess that thanks to this is a webinar and not a real seminar, you can read the values here. And these are the detection limits of all different studies. So you see the detection limits in nanograms per liter could be even 200,000 or 800 and 500. When we saw that we needed a 2 nanogram liter to be able to measure something. So it was really, let's say, terrible. And my conclusion was that it didn't make sense. That the author solved the problem of developing methods that were useless by saying that they tested waters that contain no bismuth, or that the bismuth was not present, or at the end they did what many people does, that is that when it doesn't work, you spike your sample with a huge amount, an unrealistic high amount, and you get something. So it was really not a very good situation. Some years later, in 2015, I was involved in a huge European project, which is a cost action. European cost actions are not research projects, but is money that is given to create networks of people working on the same subject. And the network was on the technological critical elements. So these elements are elements that are used in high-tech applications. Usually they have not been much used in the past. And this classification of TCEs includes different elements. It depends on the political situation, because in fact it's a geopolitical classification, it's not a scientific classification. Okay, so in this context of this cost action, I decided to have a look at the elements among these technological critical elements, among these TCEs, the ones that were even less studied, so which are the ones that appear colored in this table. And so I went back to these results from the European geological surveys for all these elements. So you have niobium, tantalum, germanium, and all the rest. And this was the percentage of values below detection limit. So again, there is a problem, because the current techniques were not able to determine the concentration, natural concentrations. And of course, these techniques this technique was ICP-MS, normal ICP-MS, which is what's normally used nowadays in monitoring labs. So we tried to go a bit further, and in collaboration with Ilya Rodushkin in Sweden, we had a look at the response and the ICP response for these elements. And for that, we took a certified reference material, a well-known, and from Ilya had many different batches, all batches of this river water. And then we analyzed them by using sector field ICP-MS at different resolutions. So you have low resolution, medium resolution, or high resolution, and then we tested different isotopes. You can see that, for example, for thallium, it doesn't matter. You can change the resolution and you get the same value. So there is no interference problem. And the same for niobium, and this is normal because, well, normal, let's say. Thallium and niobium are good in the sense that they have only one isotope. Well, thallium has two, but one is 0.1%, so it's nothing. And luckily, they don't have many interferences around. But if you look for gallium, the difference was huge. So depending on the resolution, you get very different concentration values. So we saw that it was not just a matter of detection limits, as we saw in the previous slide, but also could be a problem of resolution of the technique, so of the presence of interferences. And this was the case for gallium. and it was also the case for germanium. So I decided to go further with germanium, and germanium has this isotopic composition. So you have quite a lot of isotopes in different proportions, and it's a difficult element because you have isobaric interferences for two isotopes and many polyatomic interferences, which are responsible for this different response that we saw in the previous slide. That is the same values that you can see here. So we move a bit further, and now in collaboration with very nice people in Prague, we explore the possibility of using ICP-MS together with hydride generation, which is really the technique they're very experts on. And so hydride generation, cryotrapping, ICP-MS. And this work has been published, but what we saw is that it's very critical, the conditions you use for your measurements, as well as the isotope that you use for your quantification. So it's a kind of trade-off in between limit of detection and interferences and the practical work, because we also had you have problems you don't expect. But for example, when you measure the pH of your solutions with a glass electrode, you contaminate your sample with germanium that is present in the glass. So there are all kinds of interesting issues around. You can find that in the publication, and we got a detection limit, which is enough for my main purpose, which was to study a natural system. So I applied this method in waters of Lake Geneva, and it's very satisfactory because it has enough detection limit, and even if the concentrations are very low. So what we did, this is Lake Geneva. In Geneva, it's here. Lausanne, it's there, and we took samples in the same place, which is where it's in what we call the small lake. This is the big lake, and this is the small lake. And every month over the productivity period. So for us, this means January to June. And we took profiles in this place where the lake is 80 meters deep, and also in the middle of the lake where it's 300 meters deep. But I always only show here the results for the 80 meters because this is not a talk about germanium. And you see, we got vertical profiles when the lake was well mixed in winter, and a nutrient type profile when the lake was stratified in going to summer. And if you compare these profiles with the silica profiles, you see that they look the same, which is the same, has been published in oceans, had never been published in lakes. And this is because of diatoms. In the blooms, in the spring blooms, you get a lot of diatoms in the surface. They consume the silica, and they also consume the germanium, which is present in this form. And because they think they just make a mistake, let's say, they take germanium at the same time as silica, so the profiles are very similar. And our method also allows us to measure methyl germanium, because germanium is present in natural systems as inorganic germanium, but also as a methyl germanium. And this methyl germanium was present in a very low concentration, even lower than the inorganic one, and it's conservative. So it means all the profiles are vertical, which is exactly the same as in the oceans. So we could show that in the lakes, big lakes and oceans, the behavior is the same, except for one issue, and is that in the oceans, you have much more methyl germanium, about 10, even 100 times more than inorganic germanium. And this, if anybody is interested in germanium, I can explain you the reason later. Here we are more on the analytical side. So it works pretty well. You can say, okay, we solved one problem. But in fact, maybe not. because something I did was to compile all published values for rivers for germanium, which is about 800 values. And why there are so many determinations for germanium is because there is a lot of people in geology measuring the ratio between silicon and germanium, germanium silicon, as a way of studying weathering, erosion, because the two elements weather in a different way, are released in a different way from the aluminosilicates. This is the reason for having so many values. But when you compare the results that have been published, something happens that it doesn't make sense. In the studies where they use, all the studies are ICP-MS, I did not mention that, but it's always the case. When it's ICP-MS with hydrate generation and no isotopic dilution, just hydrate generation, the median value of all over the world is 5.9. In the studies where they use hydrate generation and isotopic dilution is 9. And why isotopic dilution? There is a community of people in geology using isotopic dilution in this type of studies. And of course, if you use isotopic dilution, you can get, let's say, good conditions for the determination, but you cannot get, of course, the methylated products. But they are not interested in the methylated products. Anyway, the difference is significant. But if you take all the studies just ICP-MS, no hydrate generation, then the median value is 21. So there is a problem there because, of course, you cannot get such big difference at changing the technique. So the amount of germanium is technique dependent, and it's kind of obvious that this is due to the fact that the people working with ICP-MS measure germanium plus a lot of interferences that goes with germanium. But this is the values that are published. So and not really critically analyzed. People just publish the value, and that's it. Okay, in our case, our method is also interesting because we have been able to put it together with small modifications that allow us to determine the speciation of arsenic, antimony, and tellurium on the same sample. So we take 10 milliliter samples and we can get all the speciation of all these elements with very nice limits of detection. And for instance, if any of you is interested in the application to arsenic, this has been published in a paper, and these values are for the same point, in fact, the same samples as the ones I showed you for germanium. So we just took one sample, and from the same sample we could study germanium and we could study arsenic. And the results for arsenic are really very, very nice. I don't know if any of you is very much knows very well arsenic, but we were able to determine arsenic that was behaving, as you see, some months in a conservative way in winter. One was well mixed, the lake was well mixed, but as soon as the productivity started, we got all kind of different profiles and behaviors. And in this case, it's also linked to productivity, but not only diatoms, but all other phytoplankton and zooplankton being produced in the lake. Notably, we were able to measure the methyl arsenic 3, because usually you get 3 plus 5. We could separate the two of them, and we also were able to measure the TMAO that behaves in a completely conservative way as compared to other elements. So it's quite nice method because you can get a lot of information from one sampling. which is, at least for us, it's an important point, because sampling is when you need to sample in the same system many times, like here in profiles, this is very cost activity. However, not all are nice. Not all is nice. For example, we are having problems with antimony speciation, but which is linked to the lack of commercial products for monomethyl antimony or dimethyl antimony. You cannot get that in. It's very difficult to synthesize that. So if any of you have these products, then I will be very happy to share. The one that you can buy is the 3-methyl, and even that is not very easy. So it's difficult to quantify, and we make the quantification and related to the quantification of the inorganic antimony and taking into account possible demethylation. But of course, this also all gives us minimum values, but not maximum values, which is kind of is really annoying. And we have another problem, which is the following, and that is also the case for arsenic. We are not the first ones to find that for arsenic, but the first ones to find that for antimony, and it's the following. These are results for antimony in Czech reservoir, and you have here the different species. Most of it is antimony 5, as predicted by thermodynamics, nearly no antimony 3. And a bit of methyl, dimethyl, and 3-methyl. But when you add all of them, you don't get this curve here, which is the addition of all of them. And this is the curve you obtain by ICP-MS, so it is total dissolved. And there is this difference, and this difference is what we call dark, but it's not necessarily dark antimony. So there is a fraction that we cannot find, and we don't know whether it's due to some problem with the hydride generation, or the estimation of the methyl and dimethyl, or some artifact. But in any case, we have this problem of dark that we have not solved that yet. And as I said, it was also we find that also for arsenic. And for arsenic had been described by Japanese people. And just to finish with my germanium, it's not because I think that germanium is very important if I discuss that in detail. It's because I think it illustrates many important points of problems that you can get analyzing these trace elements, other trace elements. And this is related to germanium digestion. And some years ago, when I was in this cost network, I found a paper that was also published by the European Geological Surveys, where they had determined germanium in agricultural soils, and they have found values. They had a lot of analysis, 4,000, which 4,000 samples is a lot, and the values they got were 1% of the usual values expected, according to UCC, to the concentration in the upper continental crust, which was kind of strange. They had used aqua regia for the digestion, which in fact follows an ISO method. Something didn't make sense, so we made some kind of experiments ourselves, because that were published some years ago already. And because the problem is, or the problem we expected, could be coming from the fact that when you treat a sample that contains germanium with aqua regia, you get a production of tetrachloride germanium, which is very volatile. So in fact, you can have big losses of your samples. In fact, you can get some, depending on how you work, you can get at most 20% of what was in your sample. So we studied a bit how to improve the situation, like using some kind of solution to take the the gases, the vapors that was coming from the solution, whether it was better to use nitric acid or sodium hydroxide. So if anybody is interested in the details, it's in the paper. But the important point is that I tried, well, the important message is that I tried to ask the people who had done the work whether they have used the aqua regia digestion open or whether there was closed system. And it was impossible to find that. And finally, I found that, in fact, there was no analytical chemist in Europe doing that because of budget problems, they had very nice analytical labs, but they don't have them anymore. So what they do is that they send that to commercial firms for the analysis. And of course, they give that to the cheapest one. And this cheapest one happened to be in Vancouver. So I called the people in Vancouver, and it was some years after the paper had been published, but they kept the records. So this was good, in that sense, a good lab. And then I asked whether the analysis had been done open or not. And they said to me that open because this was the option chosen by the geologists in Europe because it was cheaper. So it's clear that there was some kind of analytical chemist missing in that, because it doesn't make sense to analyze 4,000 samples and get results that mean nothing. So I think that it's a nice example of the importance of having an understanding of the method and people understanding the method behind the analysis. Okay, I'm going to move to the second chapter of my talk, which is about time series data. Usually if you are just an analytical chemist, you get your samples, you analyze them, and it's so far so good. But this data usually is needed for something. And in our days, the data is often needed to be compared with previous one. I mean that if you go somewhere and you get a value, very often the question is, it's more or it's less than it was a year ago. Are we improving, or is the situation degrading, or what's happening? And this is an example that you are used, which is not an example about trace elements, even not about any concentration, it's temperature. And this is the evolution of temperature in Switzerland since the 1880s until today. And of course, if we are able to say that the situation is not good and that it's getting warmer, is because we are able to compare our current data with the data that we had before. So this is a data series. Of course, as I said, it's not a data concentration, but still is a time series. This is the same time series, but shown in a different way. This is about more about communication and than science, but okay. There aren't many long concentration time series, and the obvious one, the most important one, is the Killing curve, that I'm sure you are all familiar with, which is the concentration of CO2 in Hawaii, and we have data since the 60s. And it's very good analytical data. If any of you are interested on the analytical side, it's a really very reliable data. Of course, this data is showing us that we are going right to the disaster, but this is another question. This is a good data, and it's data for CO2. But when you go to data in waters, for example, this you don't have much data available. A classical paper, or classical in the sense that is often cited, is this one, that is about the presence of gadolinium in San Francisco Bay. And it's a 20 years record, which it was a 20-year record when it was published, which is quite a lot for trace elements. because, of course, you can measure that when you have the technique to do that. And we could not measure that many years ago when our techniques were not available or not sensitive enough. This is also a very nice example because you have a big increase of gadolinium. This big increase of gadolinium is due to the use of gadolinium in contrasting agents in medicine. So this is this increase that was observed there is now observed in all water systems in Western countries. So it's not a particular case for San Francisco. Excuse me. So we tried to also to see whether we could detect any evolution of trace element concentrations in our lake, Lake Geneva, and by using a series of data that is quite exceptional. It's data that is provided for the Canton Geneva, has been measuring every month for quite a lot of years the concentrations in the same point where I showed you the data for germanium and arsenic, and they have gone there every month and measured quite a lot of elements, of course, by using ICP-MS in a multi-element determination with all the advantages and disadvantages, mostly disadvantages of using multi-element. But we tried to see whether this data that exists since 96 could be used to extract some environmental related consequences. So here you have the data for 6 elements, which is antimony, molybdenum, strontium, cobalt, cadmium, and lead. As I said, for all these years, the same point, more or less, except when the weather conditions were not good enough for the same point of the lake. Now, the first thing you can see, obviously, is that you have 2 colors, and that the 2 colors, the data is not exactly behaving the same way. The 2 colors correspond to different ICP-MS machines. So this was the first they bought in the canton, and this then in 2006 they changed, and they bought a new one, which was better. And it was obviously better because the dispersion of the data is lower. So this already shows that this is let's say a tricky business, because you have, if you want to study the evolution of the concentrations, it's going to be very difficult to compare the data in the first and in the second period. And this is something that looks evident because I told you that they were 2 different machines. But very often when you have access to long series of data that usually have been collected in monitoring with a monitoring objective, you have not much information about whether they have changed the machine, what's going on there. So you can sometimes, if you see all the data without the difference in color and with knowing the machines, you can easily decide that there was something very important in the environment that was modified at this moment there. So it's quite complicated, and it shows the importance of having, on one side, good analytical data, but also good communication skills and good housekeeping of the data. Look at this. This is arsenic in the same point of the lake, exactly the same. But here you have 3 colors, and it's because here I also show the data for the third ICP-MS they bought. And you see that the technique is improving. I mean, the instrument is better, but that the data becomes more and more difficult to treat altogether if your objective is to know whether it's the amount of arsenic in the lake is improving or decreasing. By looking at this, we spend quite a lot of time trying to understand this V in the middle of the red. And I can tell you that some people spend quite a lot of time trying to see what had happened in the lake at that moment in 2011. But it turned out that we had access to the CRM analysis. So these people, each time they analyze the samples, of course, they analyze a certified reference material at the same time. And here you can see all these points in kind of yellow or orange are the values for the CRM. And the same these blue ones. It's a different column because this is SLS4 and this is 5. But you see how the analysis of the CRMs show that what you show in the data, in fact, is instrumental. I mean, the dispersion here was instrumental, which already suspected, but even this kind of V here, this decrease and increase is instrumental. So it's not something going on in the lake. And that this kind of gap in between the second and the third instrument is also instrumental. So this shows that to which point, if we want to interpret any environmental data that exists, we need to do that, or we can only do that if we have all these underlying information, like the values of the CRMs, which is never published, or direct contact with the lab that had obtained the data, which is not so easy when the data comes from the 90s. So people are not working there for 30 years, the same person for sure. So this, for me, illustrates very well the importance of analytical chemistry and the importance of keeping track of all the results and in a lab and the methods used. I'm just going very fast because I'm a bit late, let's say. We did the same thing for the organic matter content in Swiss rivers, also using monitoring data. In different, each one of these is a different river, and in black you have the DOC, and in gray the TOC. And we detected that in some rivers were increased, in some rivers were decreased, because when you apply non-parametric methods to that, you can get this information. And then we were surprised when to find that it was like well known that all over the world there was something calling global browning going on, which means that all the rivers in the world were having more organic matter. And this, we even wrote a letter to this journal saying, no, there is no global warming. In some places increase, in some places decrease, and we have no data for the southern hemisphere anywhere, so you cannot call that global. And analyzing all the papers published, we found that in many cases was a lot of cherry picking. So as when people saw that it was increasing, they said, oh, it's increasing, and forgetting that in 10 more cases it was decreasing. But the main point was that there was no information, analytical information. The values were given like that, and no way of knowing which had been the technique used. So again, if we want to go further, we need good analysis and good analytical methods and good keeping of methods and keeping of the information. And this leads me to the last part of this talk, which is about 5 minutes, and is the need to change publication and dissemination practices. This has nothing to do with trace elements, really. It's more general as a subject. But I think that if we don't change the way we keep and we publish, we keep information and we publish this information, it's a lot of energy wasted. I was surprised again by this sentence that I found in a very different context, and is about the regulation in medicine, drug regulators, when an important person there said that they don't use what it's in scientific journals. It's because obviously the information that is there is not enough. But we as a scientist, we use publications as the way of disseminating our information. So, and I'm sure it's the same for people working in drugs. So this means that the publications are not really fulfilling the role. And this is something that we have all experienced. If you, at least all the people who have been preparing reviews, they all know that sometimes there is data, but it's not shared. And sometimes there is data, but nobody knows where it is. Or it's all has. There are all different possibilities, but the access to the original data, it's incredibly difficult. In that context, I'm going to make a bit of advertising of FAIR principles that I'm pretty sure you all know about, but I think that they are very, very important. I mean, to have data that we can find, that is accessible, that we can compare. And we have been trying, but at the same time, this imposes some kind of extra work for the people publishing. People say, or scientists say, oh, it's already very difficult to publish. And if on the top of that, we need to include even more information, it's a nightmare. Because in practice, what's happening, and this is a different context, this is microplastics, and this is a slide from a presentation that I did last year in a conference. The reality is that in this field where the publications are exploding, the number of publications where the data is available in a repository is nearly nothing. So in fact, all this data, when you try to reuse it, you cannot. Because you need the data, but you need this, all goes with the data. So the methods and all kind of information around. And in this metadata, which is known as metadata, again, analytical chemistry has a role very important to play, because a lot of this metadata concerns methods. We are very relatively active trying to prepare data sheets for, in the case of microplastics, but also in other fields, very simple data sheets that the people, when submit papers, just fill up, and in kind of a standardized way, and like that, we are all sure that all the necessary data is there. Of course, first you need to know which is the necessary data, and like geographic location in the case of environmental studies, sample identification, methods, definition of microplastic, because this is for microplastics. And but if you provide people with an easy way to enter the data, maybe the situation will improve. Otherwise, most of the data that is being published is just not, it's useless. So I think that it's necessary to establish some kind of dialogue, first in the scientific community, in the different fields, for the people to decide what's needed. I mean, what's all this data, metadata that should be provided. Then there is a dialogue between data scientists and researchers, because there are some constraints in the way the data should be provided for being reused. For example, PDFs should be avoided, and we are all using PDFs all the time. And then there is also a dialogue needed with publishers, because unless publishers, not forced, but oriented amongst people in some ways, this is not going to happen. And the message here is, of course, I guess everybody's more or less convinced that the data should be available, but what I would like to stress is that just not data, it's also methods that should be made available in a clear way. So I think that this is more or less all what I wanted to say to you. I just wanted to add something that maybe it's a bit out of the subject, but not completely, because it's a subject that I wanted to include. This year it's a 25th anniversary of a publication of this paper. This paper was by Clemens Reimann, which is here. Clemens is not dead, So I'm just going to say that, because when you say that you are doing something in honor of, it's because the person is not there anymore. It's not the case. It's retired, but not there. And it's something that is I'm pretty sure that all of you do, which is using enrichment factors. And there is a lot of reasons not to use that, and a lot of analytical reasons behind. So just if you have some time, just have a look at this paper. And this is about all I wanted to explain to you. And I'm very, very happy to answer your questions in case you have any.